Right. Good afternoon, everyone. We are recording now. So last lecture we were discussing complementary slackness conditions, right? And we proved the complementary slackness theorem for a specific class, which is maximize C transpose X subject to AX less than equal to B and X non-negative, and it's dual, right? But the reason I chose this form is because in this form you have both possibilities. You have inequalities in both the primal and the dual, and therefore you will get two types of complementary slackness conditions. However, if it was AX equals B and X at least 0, the standard equality form, then because AX equals B is always tight, you won't get one of the two types of complementary slackness conditions. Okay, we'll see an example of that later. Right, so that's the reason I chose this form, so that we have both possibilities. And the point is that actually complementary slackness holds for any primal dual pair. Okay. So what do the conditions say? The conditions would say that for every constraint of the primal, either the corresponding constraint holds tightly, right? It's a tight constraint for X bar, or otherwise the corresponding dual variable has to be equal to 0. And similarly, either the dual constraint holds tightly or the corresponding primal variable equals 0. We are not going to prove the general version for the same reasons as I have mentioned before, that there are no novel mathematical ideas in proving the general version. So in most of these theorems, we will prove for specific types of LPs, and we will assume that it is true for arbitrary primal dual pairs. Okay, so I just want to do one quick question of an application, or let's say a concrete example of this general theorem. Okay, so here is a primal dual pair, and I just want to write down the CS conditions. Okay, so the primal is minimize -330 X subject to the following constraints: 313, 503, 517, and 831. And the constraints are all types of constraints. And the variables are also all possible types of variables. Sorry, X3. Okay. And let's write down the dual quickly. I hope everybody is comfortable writing the dual. So the primal is a minimization problem. So the dual is going to be a maximization problem. And we get 0, 5, 6, 7 times y over here, subject to, let's take the transpose of this matrix. So we have 313, 503, 517, and 831. And on the right hand side, we have the objective function from the primal. And let's put down the inequalities next, and then we also have y1, y2, and y4. Okay. So let's see. Well, this is a minimization problem. So less than equal to is going to be our natural constraint. And so this one, y4, is going to be greater than equal to 0, because that would be the natural variable, right? And equality constraints give you free variables. So y2 and y3 are free variables. And this one here is an unnatural constraint. So y1 should be less than equal to 0. Sorry, wait a second. Did I mix that up? It's a minimization problem. Minimize x, subject to x at least 5. Yes, in fact, I made a mistake. This is actually natural, and therefore this should be non-negative, and this should be non-positive. My bad. Yeah. Okay. Does everybody agree? Okay, I still need to put down the constraints inequalities. So x3 is free, so the third constraint is going to be equality. X2 is non-negative. So for a maximization problem, this would be less than equal to, and this would be greater than. Okay. All right, so if this is our primal dual pair, I just want to apply this particular theorem and write down the complementary slackness conditions. All right, so the CS theorem for this particular primal dual pair tells you that if x bar is a feasible solution to the primal, y bar is a feasible solution to the dual, then x bar is optimal for the primal and y bar is optimal for the dual if and only if the complementary slackness conditions hold. Right? So let's write these down. So what are the complementary slackness conditions for these two vectors, x bar and y bar? Can someone tell me how many complementary slackness conditions do we have? Like how many individual constraints, conditions do we have? Right? We have got 4 constraints here, and we have got 3 constraints over here. Some of these are equalities, so they won't give us anything, right? Because what are you going to say? Either the constraint holds tightly, which it always holds, so it doesn't even make any sense to write down the OR statement. So we are going to get one condition per inequality in these constraints. So the first row in the primal tells you that either 3x1 plus x2 plus 3x3 is equal to 0 in this case because it is the right hand side, or the corresponding dual variable y1 bar is equal to 0. Right? So either 3x1 bar plus, let's see what it is. X2 plus 3x3 bar. Or the dual variable corresponding to this constraint sorry, my OneNote is hanging. Okay. Or the dual variable y1 bar is equal to 0. Okay, let's look at the next one. These two are equality, so they don't give us anything. The last one here is 831. Either that is equal to 7, or the last dual variable y4 bar is equal to 0. So okay. And let's see what we get from the dual. So dual's constraints. So the first constraint is an inequality and the second one is an inequality. So we will get two conditions. And the last one is an equation, so we won't get anything. Right? So either 3558 equals minus 3. So 3 times y1 bar plus 5 times y2 bar plus 5 times y3 bar plus 8 times y4 bar equals minus 3, or the primal variable x1 bar is equal to 0. And then we have one more for the last condition. For the second constraint. 1013 at most 3. Or the corresponding primal variable equals 0. Okay. So does everybody see how we wrote down these conditions? Okay, so if you have any feasible solution to the primal and the dual, you can also check optimality by just looking at the CS conditions. And right now, it may seem a little bit unclear why we need to check these conditions. Why can't we just check whether C transpose X bar is equal to B transpose Y bar, right? Because we know what the vectors are, so we can just compute. And if they are equal, then we know they're optimal. But this way of looking at it is going to be particularly useful when we look at combinatorial optimization algorithms. In fact, most of the combinatorial optimization algorithms we'll be looking at, they will make use of CS conditions. So the fact that you want the CS conditions to hold at the end of the algorithm will be sort of the plan throughout the algorithm. So we will try to make sure that at each step of the algorithm, we are moving towards making the CS conditions hold. Okay, I'll just leave it at that. It will become clear once we see the algorithms, how the CS conditions are really being used. Okay. All right. So are there any questions or concerns regarding any of what we have discussed so far? Does everybody see how complementary slackness conditions work? Given any arbitrary LP, I hope you can write them down yourself. Okay, so that's all for complementary slackness. I want to move to the last topic in duality, after which we'll be moving to module, what would it be? 1, 2, 3, 4, 5, right? So this will be the last topic in module 4. Okay, so remember, how did we start with linear programming? We started from geometry and convexity. We in particular started with the feasible region, and we noted that the feasible region of any linear program is a polyhedron, right? And then we went on to simplex, certificates, duality. So today we are going to again end with, today and probably the next lecture included, we are going to end with geometric stuff. We are going to look at the geometric characterization of optimality, right? So we have reached the end of the linear programming part of this course. All right, so let's consider an example. In fact, an example that we started linear programming with. I'll remove 2 of the constraints to make it a bit simpler. Consider the polyhedron defined by the following constraints. So in our first example, we had 5 constraints, but now I'm just going to keep 3 of them. So let's say we have these 3 constraints. Okay. So I've removed the non-negativity constraints that were there in our first example of linear programming. And let's draw the feasible region. Actually, let me change the rule lines. Oh. Okay, so the first one is 2x1 plus x2 less than equal to 9. So this is the point 9. And the next one is x1 plus x2 less than equal to 7. So that's going to be this point and 5, 6, 7 here. And the last one is minus x1 plus x2 equals 5. So that's going to be oh, I think I might have made a mistake. Yeah, sorry. I think I messed up. Yeah, sorry. So I think there is some issue with my OneNote today. I'm not really sure what's going on with it. So I think I meant to choose 4.5 here, this point, and 1, 2, 3, 4, 6, 7, 9. Okay. So this is my first line actually. And then I have 7 over here and 1, 2, 3. Okay, so that would be 7 over here. Yeah. And 1, 2, 3, 4, 5. Yeah, okay, this looks much better. All right. So our half spaces are this one, and this one. And so the feasible region is going to be, let me just put a new color. And let me shade it in red. Right, it's going to be a polyhedron and not a polytope because it's unbounded on one side. Okay, so this is our polyhedron defined by these three constraints. And so the feasible region depends entirely on the constraints, right? However, optimality also depends on the objective function, right? And in fact, that is exactly what we want to ask. For what objective function would a particular point in the feasible region become an optimal solution? Okay. All right. So, and notice that there are two extreme points here. One of them is this point. This is 1, 6, if I'm not mistaken. So this is our x1 and this is our x2. And this point here is 2, 5. Okay. All right. So let's suppose we are considering maximize C transpose X subject to the three constraints, which I have labeled as 1, 2, and 3. So the constraints are the given constraints 1, 2, 3. So my question is, for what choices of the objective function C, or C transpose if you like, does the given feasible solution become an optimal solution? Okay. And I want to give you an example of some possibilities. So let's consider the two extreme points. We are going to discuss something that applies to all feasible points, but I'm looking at the extreme points just for the sake of example, right? Also because in some sense, they are the most interesting points in our polyhedron. We know that whatever objective function you choose, one of the extreme points has to be an optimal solution. So consider x bar 1, 6 and consider x bar equal to 2, 5. There are two possibilities I want to look at. And I'm also going to consider two objective functions. The first one is 1, 2, and the second one is 5, 4. Okay. So in the first case, we are maximizing x1 plus 2x2 subject to the given constraints. And in the second case, we are maximizing 5x1 plus 4x2 subject to the given constraints. And let's see what the values of these points, these are feasible solutions, right? Because they are extreme points of our polyhedron. So in particular, they are feasible. So I want to compute the value for both of these choices of objective functions. So let's look at the first one. So let's look at what this is. Can someone tell me what is this quantity? What is the value of x bar if we choose the objective function as x1 plus 2x2?
$13.
13. Okay. What about this one? It's 2 times 1 plus 5 times 2, right? So that would be 2 plus 10, 12. Can someone tell me the two entries here?
I think the first one should be 29.
Right.
And the next one should be 30.
Right. Exactly. Thank you. So observe that, and we know by our discussion about the simplex method and everything, that for whatever objective function you choose, some extreme point will actually be an optimal solution, because simplex always finds basic feasible solutions, which are also extreme points, as you should know by now by our assignment 2, right? So in particular, for this choice of the objective function, x bar 1, 6 is actually an optimal solution. However, for this choice of the objective function, it is not an optimal solution. However, x bar equal to 2, 5 is an optimal solution. Right? So I hope now, in context of this example, the question becomes clear what we are asking. For what choices of the objective function does a particular feasible solution become an optimal solution? Okay. All right. So let's see how we can proceed to answer this. So let's consider one example. So I'm going to choose x bar as 1, 6 for the sake of discussion. And let's consider C1, C2 as our objective function vector. Maybe I should consider C transpose equal to C1, C2. And let me also write down the general form here. So we are maximizing 1, 2, x subject to the given constraints, which I'm going to write down in the usual matrix vector format. And what is the dual of this going to be? It's going to be minimize 975y subject to 2, 1, minus 1, 1, 1, 1 y equals 1, 2, and y's are going to be non-negative. Okay. So now let's suppose we want x bar to an optimal solution. For x bar to be an optimal solution, by strong duality, there exists y bar, which is also an optimal solution to the dual, such that C transpose x bar is equal to B transpose y bar. Right? But we are not going to actually make use of this part. I actually want to make use of complementary slackness. So by complementary slackness conditions, what do we get? Let's try to, right? Because if they both are going to be optimal solutions, they both need to satisfy the complementary slackness conditions. So let's figure out what are the tight constraints of x bar. Because if a constraint is not tight, then the corresponding variable in the dual has to be 0. So let's look at the tight constraints of x bar. Right, so x bar is 1, 6. So if you plug in 1, 6 over here, which ones are the tight constraints? Can someone tell me? Is it the first one, or the second one, or the third one? Oh, sorry, I forgot to put an X here. Right, so the first one is 2 times 1 plus 1 times 6, which is equal to 8, which is less than 9. So that's not tight. However, notice that the second and the third constraints are both tight. So since the tight constraints are the second and the third one, we know by complementary slackness that the constraint that is not tight, that dual variable has to be equal to 0. Does everybody agree? If x bar has to be an optimal solution, then the dual variable has to be 0. In fact, I think I made a mistake over here. I did not want to write 1, 2. I have fixed the x bar, but I don't want to fix the objective function. So I'm going to write C1, C2 over here. right? Because we don't know what the objective function is. Okay. Are there any questions at this point? So now what does that mean? If y1 bar has to be 0, that means that I have a system in two equations. If you look at the right hand side here, what does y1 bar equal to 0 means? It means that the first variable is always 0. And so I just need to look at the last two columns here. And y2 bar and y3 bar, when plugged in, should give me C1, C2. Right? So that means that this matrix times y2 bar, y3 bar should be exactly equal to C1, C2. For some y2 bar and y3 bar which are non-negative, because non-negativity is in our dual, right? Because the x's were free variables. Are there any questions at this point? So what does this mean? So I want you to think about it in a slightly different way in case you aren't used to it. Right, so we are multiplying a matrix by a vector on the right hand side. Right? That just means that we are taking a linear combination of the columns to get C1, C2. Right? In particular, this means that y2 bar times 1, 1 plus y3 bar times minus 1, 1 is equal to your objective function. Right? For some y2 bar and y3 bar non-negative. Okay, so now I want to use this to figure out for the two choices of the objective function whether x bar will be optimal solution or whether it will not be an optimal solution. Okay, so now let's suppose I consider the two possibilities. So the first possibility is 1, 2, and the second one is 5, 4. Okay, and if you solve, basically you have two equations here, right? You have the equation that y2 bar minus y3 bar is equal to C1 and y2 bar plus y3 bar is equal to C2. So if you consider C1, C2 as being the vector 1, 2, and you solve this system, you will get that y2 bar is equal to 3 over 2, and y3 bar is equal to 1 over 2. And in particular, these are non-negative. And this implies that your point x bar will actually be an optimal solution. However, if you consider 5, 4, let's just solve the system and see what happens. Let me just convince you. Y2 bar minus y3 bar is equal to 5 and y2 bar plus y3 bar is equal to 4. Right, so what do you get? You get that y2 bar, 2 y2 bar is equal to 9, so y2 bar is 9 over 2. And now if you look at the second equation, 9 over 2 plus something is equal to 4, so that something has to be minus half. But remember, we want the y2 bar and y3 bar to be non-negative. And so this implies that x bar is not an optimal solution. Right? So what happened? We were able to write the objective function as a certain type of combination. So what is this combination? It is a non-negative linear combination of the rows corresponding to the tight constraints. Remember, the rows corresponding to the tight constraints are exactly these two rows, which became the columns in the dual. Right? So if you are able to write down the objective function as the non-negative linear combination of the rows corresponding to the tight constraints, then for those choices of the objective function, your solution x bar will become an optimal solution. And otherwise, it will not be an optimal solution. Does that make sense? Does everybody see what happened here? Right? We simply applied complementary slackness and we arrived at this conclusion. So we haven't proved the theorem I'm about to state. We will prove it next time, or you might prove it on your assignments. I haven't decided yet. Right? It's an application of complementary slackness. So let me just put down the theorem, but before I put down the theorem, I need some definitions. Okay. All right. So given a set of vectors A1, A2 up to AK in Rn, we are going to say that the cone generated by these vectors is the set of all vectors that can be written as non-negative linear combinations of the given vectors. Right? So it's the notation we will use is simply cone of A1, sorry, it's going to be summation I going from 1 to k, lambda I, ai, where all the lambda i's are non-negative. Okay, and this kind of a combination is called a conical combination. So we have already seen convex combinations. You all are familiar with linear combinations. So this is yet another type of combination which happens to be really important. Okay. All right. And let's see if I can just find the theorem. Yeah. So theorem 4.7, supposing you have a feasible solution for the following linear program, maximize C transpose X subject to AX less than equal to B. Remember, whenever we are discussing geometry, we are treating all constraints in the same way, right? It is only when we are doing more algebraic stuff that we distinguish between the regular constraints and the non-negativity, non-positivity constraints. But whenever doing geometry, it actually makes more sense to just consider all constraints as being sort of the same. So even if you have non-negativity constraints, you can throw them into this matrix and you can declare the variable to be free. Okay, so you can write any linear program in this form. maximize C transpose X subject to AX less than equal to B. So the theorem says that X bar is an optimal solution. So yeah, it's already a feasible solution. So it says that it is an optimal solution if and only if the objective function C belongs to the cone of tight constraints at X bar. So what does this mean? The cone of tight constraints means that you look at the tight constraints for your particular solution, right? So in our example, the tight constraints were 2 and 3, and you look at the rows corresponding to those two constraints. I think there is some error here. So what were our constraints? 2, 1, 1, 1, and minus 1, 1. Sorry. Yeah, this is a minus 1 and this is a 1. Okay. Right? So you look at the tight constraints for this particular solution, and the corresponding rows are 1, 1, and minus 1, 1. So if your objective function C1, C2 belongs to the cone formed by these vectors, then X bar will be an optimal solution. Otherwise, X bar will not be an optimal solution. So that's what it means. So for our example, if you consider X bar as 1, 6, let me just say, if X bar is equal to 1, 6, then the cone of tight constraints at X bar is the cone of the vectors. So let's write down our constraints. X1 plus 2x1 plus x2 less than equal to 9, x1 plus x2 less than equal to 7, and minus x1 plus x2 less than equal to 5. So in this case, the tight constraints are the second and the third one. So the cone is 1, 1 and minus 1, 1. So the cone of these two vectors. All possible non-negative linear combinations of these two vectors. Right? And if X bar would be equal to 2, 5, which was the other point we were considering, then the cone of tight constraints at this vector 2, 5. So let's plug in 2, 5 into these three. And what do you get? The first one is tight. So you get the vector 2, 1. And the second one is also tight. So you get the vector 1, 1. And the third one is not tight. All right. So whenever the objective function belongs to the cone of tight constraints, you know that the feasible solution you are considering is an optimal solution. So this is a geometric way of looking at optimality. And I just want to show you a drawing of what the cone looks like. You will kind of understand why it's called a cone. So let's see. Let's look at 1, 1 minus 1, 1. So if this is my x1 and this is my x2, 1, 1 is here, right? Let's say this is 1, 1. And minus 1, 1 would be here. And notice that if you take multiples of 1, 1, they will all be, if you take non-negative linear multiples of 1, 1, they will be all on this line. And if you take non-negative linear multiples of minus 1, 1, they will all be on this line. And the cone is exactly what you see here. So all possible non-negative linear combinations of these two vectors is going to be this region. You can just check for one point whether it belongs to the cone or not, and by that you can decide whether you should be looking at this side or whether you should be looking at the other side. Right? That's an easy way to check. And so what the theorem is saying is that if x bar is equal to 1, 6, then for all the objective functions that belong to this region, x bar will become an optimal solution. And for all other objective functions, x bar will not be an optimal solution. Notice that 0, 0 is in the cone of tight constraints, which makes sense because if your objective function is just 0, then every point should be an optimal solution, right? Because the objective function doesn't mean anything, right? So let's look at the two vectors we were considering for the objective function. So one of the vectors we were considering was 1, 2, and the other one is 5, 4. So let's see where they are in this drawing. So 1, 2 is going to be, if this is 1, this should be 2. So this is the vector 1, 2. And 5, 4, where is that? If this is 1, 1, this would be 2, 2. Let's see, this would be 2, 2, 3, 3, 4, 4, and 5, 4 is over here. So for the vector 1, 2, x bar becomes an optimal solution because it is in the cone. However, for the vector 5, 4, x bar is not an optimal solution because 5, 4 is not in the cone of tight constraints at x bar. Right? And let's see if that matches our observation. For 1, 2, x bar is an optimal solution. However, for 5, 4, x bar is not an optimal solution. Right? Are there any questions or concerns regarding this theorem? So we haven't proved it. We will either prove it in the next lecture or I might just give it to you as a do-it-yourself problem. Sorry, on the assignment number 4. Next, it can be proved quite easily using complementary slackness. So this is a geometric characterization of optimality. All right, and I want to give you a do-it-yourself problem to use the cone of tight constraints and try to figure out for yourself what's going on. So okay, so here is some do-it-yourself problems. For the objective function c equal to 5, 4, use theorem 4.7 to decide which ones among 1, 6 and 2, 5 are optimal solutions. Okay. And also let's say x bar is equal to 4, 1. So this is a feasible solution for the linear program we considered today. So I want you to check which choices of C1, C2 will make x bar equal to 4, 1 an optimal solution. And I want you to do the same thing for another vector, which is 2, 2, which is also in the feasible region, right? So I've given you two vectors which are in the feasible region, and I want you to use theorem 4.7 to figure out which choices of objective function will make these points optimal solutions. So all right, and I should probably mention that if your tight constraint set is empty, then the cone is just the zero vector. Okay, so maybe that will be useful. So a remark, the cone of the empty set is simply the zero vector. That's your entire cone. Okay. All right, so that's all for today. I think I went a bit over time. Sorry about that. But yeah, and we will either prove the theorem in the next lecture or I might just put it on the assignment. I still haven't decided. It's an easy application of complementary slackness. Okay. All right, so are there any questions or concerns? I'm here for another 10 minutes. The lecture is officially over. Okay, so I'll stop recording.